We constantly guess what the future will look like, but we rarely ask how it will be funded. Let's run the numbers. The moon has been reachable for over half a century, yet there is still nothing permanent up there. Every few years, a new plan emerges. Budgets are announced, prototypes get tested, and then the funding dries up. The rockets improve, but the economics do not seem to follow. The question that keeps returning is not whether we can get there. We clearly can. The question is why the incentive to stay never materializes once the initial excitement fades. Most discussions focus on engineering. Can we build the habitat, mine the regolith, keep the crew alive? Those are real constraints, but they are not the binding one. The binding constraint is economic. Who pays for the colony once the political will expires, and what keeps it running when no government budget line guarantees the next shipment? So here is the promise of this analysis. By the end, you will understand what specific economic conditions must exist before a moon base becomes anything more than a temporary outpost. The first thing to understand is the sheer cost of moving mass from Earth to the lunar surface. Every kilogram sent requires fuel, structure, and launch capacity that must also be lifted. This creates what engineers call a gear ratio on cost. You do not just pay for the cargo, you pay for the fuel to lift the fuel that lifts the cargo. Each kilogram multiplies the expense. Now, under current analysis, supporting even a small permanent lunar settlement would require something close to 4,000 metric tons of goods delivered on a frequent and reliable basis. That logistics requirement is the bottleneck. It is not a theoretical abstraction. It is a supply chain that must operate continuously, and every interruption is an existential risk to the colony. When everything has to come from Earth, the colony has no independent economic life. It consumes subsidies. It does not produce value that pays for its own continuations. Interestingly, this is not unique to space. Every frontier colony in economic history faced the same test. Could it generate enough local surplus to survive without the mother country writing the checks? To frame this properly, we need to separate two models. The first is the government as sole customer model, where one or a few space agencies fund everything and the colony exists at their discretion. The second is a commercially self-sustaining model. Under this model, private actors produce goods or services on the moon that someone is willing to buy at a price that covers the cost of production. The transition between these two models is the critical economic threshold for colonization. Until the colony crosses that threshold, any withdrawal of government funding means the colony ceases to exist. So what could the moon actually produce that is worth selling? The leading candidate is propellant. Water ice exists at the lunar poles, and water can be split into hydrogen and oxygen, which are rocket fuels. Producing propellant on the moon rather than launching it from Earth could, under certain models, reduce the cost of deep space missions by 50 to 80%. That is a significant potential advantage. But that advantage depends on assumptions. The competitiveness of lunar propellant turns on two variables: the cost of transporting capital equipment to the moon, and the volume of propellant demand in space. If it costs too much to send the mining and processing equipment, the break-even point moves out of reach. If demand for propellant in orbit is too low, there is no customer base. Under this assumption, the viability of lunar propellant is not a settled question. It is a conditional economic scenario that depends on cost curves and demand curves that have not yet converged. Now let us build the causal chain. The fundamental problem on the moon is extreme scarcity. There is no atmosphere, no liquid water on the surface, no organic soil, and no existing industrial base. Under those conditions, every input has to be either imported from Earth at enormous cost or manufactured locally from raw regolith. And local manufacturing requires capital equipment that itself was imported. This creates a bootstrapping problem. You need infrastructure to produce resources, but you need resources to build infrastructure. On Earth, this cycle resolved over centuries of gradual accumulation. On the moon, there is no time for gradual accumulation. The colony must reach a production threshold fast enough that the subsidy does not expire before the local economy begins generating its own surplus. Follow the incentive structure. If the only customer for lunar output is a government agency, The colony's survival depends entirely on that agency's budget cycle and political priorities. The moment political priorities shift, the funding disappears, and there is no local revenue stream to fill the gap. This is the core structural fragility of the sole customer model. For the colony to survive a budget cut, it needs multiple customers, and for multiple customers to exist, there must be a product that more than one buyer values enough to pay the production cost. That product, in most current economic models, is propellant. Lunar-derived rocket fuel intended for missions heading to Mars, to asteroids, or to refueling depots operating in cislunar space. The logic is straightforward. If you can make fuel on the moon, you do not have to launch that fuel from Earth. You bypass the gear ratio problem at its most expensive point. But here is the constraint. The production mass ratio matters enormously. How many kilograms of regolith must be mined and processed to produce 1 kilogram of usable propellant determines unit cost. If the ratio is poor, you need more mining equipment, more energy, more maintenance, and more crew time. Each of those inputs was itself imported from Earth. The costs compound rather than shrink. So the economic viability of lunar propellant is not fixed. It sits on a curve. At one end, cheap launches and abundant demand make it worthwhile. At the other, expensive capital transport and weak demand make it uncompetitive. The colony's fate depends on where on that curve the real conditions land, and critically, on whether the colony can influence those conditions through its own production choices and efficiency gains. This is where incentive design enters. A colony that only responds to government purchase orders has no reason to innovate. Its survival depends on political loyalty, not productive efficiency. A colony that faces market competition, however, has an immediate incentive to lower unit costs, find new customers, and develop new products from available lunar materials. Scarcity sets the price, but competition drives efficiencies. Here is the counterpoint. Reusable launch vehicles may undercut this entire argument. If next-generation rockets reduce Earth-to-orbit costs dramatically, launching propellant from Earth could remain cheaper than producing it on the Moon. This is a real competitive threat. The 50 to 80% cost advantage of lunar propellant is not guaranteed. It depends on current launch costs remaining roughly where they are, an assumption that may not hold. There is also a scope limitation. Propellant is one product. A colony dependent on selling a single commodity is vulnerable to price swings, demand shifts, and technological substitution. A rational exception exists, though. If the colony can diversify into construction materials, rare earth processing, or oxygen production for life support, the economic base widens and the risk of single product dependency decreases. But diversification itself requires additional capital investment, which must be justified by demand. And demand for these secondary products in space is even less established than demand for propellant. So the thesis is bounded. Local incentive-driven production could work, but only under specific conditions. The gear ratio on capital transport must be favorable, demand sufficient, and the colony must not depend on one product. What validates this framework is that frontier settlements tend to follow the same pattern. The ones that survived found local resources with external buyers. The ones that did not remained subsidy camps until the subsidies ended. So let us return to the opening question. Why is a moon base so hard to justify economically? The answer is that the economics require a transition that no single policy can guarantee. The colony must move from being a government expense to being a self-sustaining producer. For that transition, someone on the moon must sell something at a price covering the full cost of production. Not the subsidized cost, not the politically negotiated cost, the actual full economic cost, including the imported capital equipment, the energy, the maintenance, and the human support required to keep production running. Change the assumption, change the equilibrium. If launch costs drop far enough, the moon competes with Earth launches on price, and the argument for local production weakens. If demand surges, the argument strengthens. The resolution is conditional, not certain. Genuine lunar colonization requires that local economic incentives become strong enough to attract sustained private capital without relying on perpetual government backstops. That means the colony needs real customers buying real products at real prices. not grants, not contracts that exist only because a politician championed them, revenue streams that survive elections. The specific conditions for this, in current analysis, include propellant demand from multiple space operators, a capital transport cost low enough to enable competitive pricing, and product diversification beyond a single resource. Without those conditions, the moon remains what it has been since the last crew left, a destination for visits, not a place where an economy lives. The incentive to stay simply does not exist yet. This is not a prediction that colonization cannot happen. It is a clear identification of what specific conditions must change for it to become economically real rather than politically symbolic. So the next time you hear about a moon-based proposal, ask one question. Who is the customer after the government stops paying? If there is no clear answer, the colony has an expiration date. Ask what the colony produces and whether anyone will buy it at a price that covers the real cost. Not the subsidized cost, the full cost, with capital transport included. Ask whether the incentive structure rewards efficiency or rewards political access. The answer tells you whether the colony is being built to last or built to look impressive for one budget cycle. Test the binding scarcity. Is it water, energy, capital equipment, or demand? Each one creates a different bottleneck, and each bottleneck suggests a different investment priority. Separate technical feasibility from economic sustainability. A technology that works in a laboratory does not become an industry until it operates at a cost below the price a buyer will pay. Compare centralized and decentralized funding structures. Does the colony get more resilient when one agency controls everything, or when multiple operators compete and cooperate under market incentives? These are not idle questions. They are the specific economic tests that determine whether a future moon colony becomes self-sustaining or remains a flag-planting exercise. The funding model decides what survives, and on the moon, more than anywhere else, the distance between a subsidy and a market is the distance between a visit and a civilization. This is not a prediction. It is a conditional economic scenario. Change the assumption, and the equilibrium changes with it. The future is just incentives at scale. See you tomorrow.